Greetings from Rutgers University. This is Ryan Sills in the Department of Material Science and Engineering. The purpose of this video is to provide a tutorial for how to use the tool we call ILDA, which stands for Interfacial Line Defect Analysis. ILDA was developed in my research group, largely by my former postdoc, Nipal Dekka, and also in collaboration with Alex Stokowski of OVITO GmbH. So ILDA is very similar to the well-known dislocation extraction algorithm, or DXA, in its functionality, but it's specifically designed to operate on interfaces, as we'll see. Okay, so before we jump into how to use it, I want to just quickly run through what is going on under the hood with ILDA. So we just had our paper on the ILDA method accepted for publication by Acta Materialia, so that should come out probably in the next week or two. This is the middle of June when I'm recording this, and this figures from that paper. So you can get more details soon as that comes out for publication. But just to give a primer here, before we do anything inside of ILDA, we have to first identify the phases and the crystals. And I'll show we accomplish that using polyhedral template matching and grain segmentation. I'll show how to do that. Then inside of ILDA, the first step is that we have to find, or ILDA has to find, coincident site atoms, or CIS atoms. So these are atoms, you can see here shown in yellow, which simultaneously are part of both crystals. So that's kind of the backbone of ILDA, is based on identifying and using these CIS atoms. So once we find these CIS atoms, the code then constructs a surface mesh using the construct surface mesh functionality in OVITO. And it uses that surface mesh to enumerate an exhaustive set of Berger circuits, which searches over the entire interface. And so that way you don't miss any line defects that may be present. And so this is where ILDA is similar to DXA, because DXA is Berger circuit based and ILDA is as well. Then we also are able, using the surface mesh, to determine the step height. So if the line defect you're interested in is a disconnection, ILDA will tell you what the step height is in the physical interface. And then finally, ILDA inserts line defect segments. So the final product is very, very similar to DXA in that you get a discrete set of lines. Each of those lines segments has a Berger's vector, but it also has a step height, which is something that DXA doesn't give you. Okay, so let's run through an example of how to use DXA and, ILDA, and in so doing we'll learn about all the different features and parameters and how they affect things. Okay, so let's go into OVITO. So ILDA is written to run in OVITO Pro, which is the version of OVITO that you have to buy a license for. And the reason it's written that way is because it uses the Python API for OVITO, and that requires an OVITO Pro license, basically. And if it hadn't been for OVITO Pro, it would have taken us much, much longer to develop the tool, because we are very heavily leveraging the capabilities inside of OVITO. All right, so the first thing is you have to have load your dump file or whatever atomistic data file you have of interest. So this is a system, as we'll see, it's a biphase system that we used as a test case when we were developing ILDA. The first thing we have to do is, we showed in that flowchart, identify phases and crystals. So ILDA is written to use polyhedral template matching. So we have to run the polyhedral template matching identifier. And so what you can see is, green here, FCC, blue, BCC. So this is an FCC BCC system. In particular, these crystals are oriented to have the Nishiyama-Wasserman orientation relationship, and this is a simulation of pure iron that we put together here using the Zhao et al. Potential. Okay, now for those that are not familiar with PTM, you basically have one parameter that you can adjust, this so-called RMSD cutoff. And so basically what this does is if you increase this value, it sort of allows the atomic structures to be sloppier, essentially. Because PTM is basically comparing an atom's local environment and determining if that environment matches any of these polyhedral templates that it has for these different crystal structures. So if you increase this, it allows sort of more slop with respect to a particular crystal structure. So you have to choose it carefully. So if, for example, if we shrink it way down at some point here, you can see we start to have atoms that are not being identified, for example, as being FCC or BCC, because we're requiring that the template be matched very, very closely. So let me switch that back to the value we had. Okay. The other thing is when you're running PTM here, ILDA requires lattice orientation, so you've got to have that box checked. Okay, so once we have identified our phases, then we have to use the grain segmentation modifier in order to separate our atomistic system into crystals or grains. And so grain segmentation requires PTM. It uses PTM to do the grain segmentation. So grain segmentation is already run. It's a pretty small system. Now what you can see here is it says it found 6 grains, and what you can do is color particle by grain to see how it's done that. Now what you can see is that there's some kind of questionable grain identification here. So it's identifying this crystal, what seems to be, to me at least, a single crystal as being 2 crystals. So you've got to be careful and make sure that, and this is related to the algorithm for grain segmentation and also to this RMSD cutoff. So you need to first be careful and make sure that your system is correctly identifying grains, or at least correctly enough, so that the main point we're interested in here is that right near the interface here, on either side of the interface, we've identified distinct crystals. And so that's going to allow us, so because the way ILDA works, it considers an interface between a set of crystals as identified by GSA here. So we got to make sure that the entire interface is spanned by a single pair of crystals, and we can see that that is in fact the case. So we're ready to go on to the next step. A few other details here around grain segmentation. One is you can see these 2 options that are checked here: adopt orphan atoms and handle coherent interfaces stacking faults. So we recommend that you check both of these when you're running ILDA, because that's what we used when we developed it and tested it. And in particular, if you have dislocations in an FCC crystal, you're going to have stacking faults present. And so you want to make sure those stacking faults are recognized as being part of the grain. Otherwise, it'll mess up how the Burger circuits are constructed. Okay, so now we are ready to run ILDA. And so for that, what we're going to do is we're going to add a Python script modifier. Now, okay, so we have this, and what we have to do now is basically load the ILDA code. Now, ILDA is available on a public GitLab repository here, and you can see it's got documentation. It has a placeholder for this tutorial, which will get posted here as soon as we've finish the recording and post it here. So hopefully the documentation is pretty good, and most users should be able to figure it out from the documentation. So you can come on over here, download the repository, or if you have Git, you can just clone it, and that way you can very easily pull updates once, as the code gets updated. Now, one other thing is, given that it was just released, I'm not going to promise that it's going to stay in this GitLab repository. We may move it to a different repository in the future, but one place you could always go to figure out where to get it is my research group's website. We have a codes tab, and here it is, and it'll always have a link to the latest code. So anyway, come here to this URL on GitLab, grab the code or clone the repository. Okay, once you do that, what you can do is take this Python script that we added, you click Edit Script, and then you go here, and it's the option is Load Script from Disk. And so here we are inside of the ILDA folder, which has the code. And if you looked in the scripts folder, there's only one script right now. It's called GUI.py. We open that, and you can see it's a very short file, and basically it references all of the other source code. So this script just serves the functionality of being sort of the interface with the OVITO GUI. Okay. Now, one thing you have to do before you run it is you have to update this path right here. So you can see this path is kind of the default path that's just from my hard disk when I've developed it. But you need to change this to use your path to the source folder, the SRC folder within the ILDA folder. So this is kind of an annoying step which we hope to get rid of in the future, but it's kind of the only time you're going to have to touch the code at all when you use it, at least for this current implementation and for the OVITO GUI. All right, so you need to update that. It'll basically throw an error at you until you update that. And what you can see right now actually is it's running, but it actually is throwing an error, which is meaningful. It says atom A and atom B are both part of grain, and it looks like the error message actually kind of has an error, which is a little bit ironic, but they're part of the same grain is what this error message is saying. So what does that mean? Well, now let's get into actually using ILDA. So what you can see on the right here, we've got the Python script selected, is there are a bunch of different parameters which you need to or can control through the OVITO GUI. Now let's start at the top. The first two, atom A and atom B, those are, think about those as the flag bearer atoms for crystal A and crystal B. That is the distinction we use in the papers. You have crystal A and crystal B, and the interface is formed between those two. So what you have to do basically to tell ILDA which crystal is crystal A and which crystal is crystal B is select an atom within each grain. Just any atom will do. So for example, you just take and hover the cursor over an atom that's just above the interface. Let's call that crystal A. And if you look down in the bottom left corner, you see particle identifier 44828. So what we have to do is just punch that in here, 44828. And we do the same thing for crystal B. So let's pick that atom. Particle identifier is 39864. Okay, it's running, and so now you can see when we run here, we don't get any error messages. In fact, it says found 368 CIS atoms. So we've successfully told it which crystals to use, and the code has automatically detected these atoms, which it turns yellow, which are the coincidence site atoms. So what we're going to do now is let's delete all of the FCC atoms so we can more clearly see the interface. There we go. And so you can see that there is a mono layer, a flat sheet here of coincidence site atoms. So these are atoms which are basically nearest neighbors, crystalline nearest neighbors, simultaneously to an FCC atom and a BCC atom. So this is a very important step. You have to find coincidence site atoms, or ILDA has to. If it can't find any, or if it only finds a few that are very far apart, it's not going to work. So you can't proceed on to actually do the line defect. So that is kind of the main drawback of ILDA, is that it requires that these CIS atoms be detectable. If you have a case where you run it like I just did, and it fails to find CIS atoms, there are a few tricks you can play. One thing you can do is increase this RMSD cutoff, and basically so that it gets a little bit more lenient in identifying which atoms are crystalline. But you've got to be careful, because if it gets too lenient, it's going to identify, make spurious phase identifications, and that is going to give you spurious coincidence sites, and you're going to get junk out of the line defect analysis. So you've got to be careful. You can't increase it arbitrarily. Now the other thing you can do, if you look here, there is a parameter called CIS tall. That is our first effort at trying to kind of make it a little more robust because the main issue where it will fail is if the interface is very thick. So what you can see, so let me get rid of this stuff here. You can see that if you just look at the interface without any ILDA being involved, there's only one sheet of unidentified atoms. So white means the structure is unknown. And so the interface is pretty thin, in other words. But if you've got a big, fat, thick region of unknown atoms at the interface, that can cause problems. It's much harder to identify where the coincidence site atoms are. So anyway, we have a initial implementation of an algorithm to try to handle cases like that. And basically what it's doing is it's trying to take the crystal above and extrapolate it down. So you can go from the crystalline atom into the middle of the interface, for example. But it's not a perfectly robust thing. It needs some development. But anyway, to use that, you just increase this CIS tall. And hopefully that, we've tested it on a couple of cases where it seems to work. And we'd be interested to hear your feedback about how effective that is. And also how, to get a sense for how often this is a problem for people that want to use ILDA. Okay, so let's go back here. We've got our coincidence sites. All is good in the world. We are able to move forward in running ILDA. So that if you want to just use it out of the box, then you just click Extract Lines. And so now you can see at the bottom here, it's reporting what it's working on, the various steps, and you can see it moves quickly, but those basically map onto these steps here. So did that first, and then surface mesh, Burger circuits, determine steps, and then insert line segments. Okay, when it's all done, you can see we get some line defects. Now there's some weird stuff here, and we'll talk about that in a second. But before we do, let's just talk about how ILDA reports this stuff right now. As of June 2023, what ILDA is doing is it's actually using the bonds structure in OVITO to insert the lines. So that, in other words, they're not going to show up as like dislocations or disconnections. They're going to show up as bonds. And so one way to see that is if you click on the bonds button down here, you can see now we have all of these bonds we've inserted. Each of these bonds has a Burgers vector property. It has a step height property. It has a terrace plane property. You probably don't need to worry about that. That's the normal for the terrace plane, which is just the plane of the interface, basically. Well, it's got a thing called a Burgers ID. Those are the main relevant things. So each of these segments here corresponds to a different bond. So for example, we can interrogate that bond. That bond has this Burgers vector, this step height, a couple of angstroms. Okay. So that's one way to interrogate the output from ILDA. Another way is, if we drag this open a little bit here, if you look in the bottom of the Python script window, it prints some stuff. What is it printing? It's printing, first of all, what's called the estimated coherent reference frame with polar decomposition. We'll talk about that, what that means in a second. It's basically a pair of deformation gradients. It gives us something about pruning the surface mesh. You shouldn't need to worry about that. That has to do with if it constructs the surface mesh for the interface and happens to get any atoms in that mesh that are not coincidence site atoms, those need to get removed from the surface mesh. And so we have this pruning step to kind of systematically go through and remove those. In this case, we didn't have to prune any. And then finally, it reports some summary information. And what it's saying is it found two unique Burgers vectors with magnitudes which differ by more than this b-tall parameter 0.01. And then it says down, each of those unique Burgers vectors gets assigned an ID. And then there's also a variant column. We'll talk about that more in a second. Total length that it found, average magnitude of the Burgers vector, average Burgers vector, standard deviation of the Burgers vector. So you may be thinking, okay, if we go back and look at the actual sort of image here, there are two distinct lines. Right? It's periodic system, so this line is coming back over here. But there's two distinct lines, okay? But what's weird is that, okay, and what ILDA does is it assigns a unique color to each ID, okay? In the middle of the same line, the ID changes, which means in principle it's a different Burgers vector, okay, first of all. So that violates conservation of Burgers vector right away. You can't have the Burgers vector change in the middle of the line. So that's strange. The other thing is, why are we talking about like a standard deviation of a Burgers vector? Because a Burgers vector is a Burgers vector. It's not statistical. All right, well, this comes to one of the most important aspects of ILDA, which is the states or the reference states that ILDA uses. So this is what ILDA is doing. It's finding a closed circuit in the physical frame of the interface, all right? So, and it does that with half circuits. So it does a half circuit in crystal A, half circuit in crystal B that closes in the physical frame. Then it uses the polyhedral template matching modifier to map each half circuit to the lattice reference frame. So this is the single crystal reference frame for each of the respective crystals. So this approach enables you to do these Burgers circuits with a biphase system like we're looking at now, to go not just with grain boundaries, for example. But then to finally get the Burgers vector, you have to map from this lattice reference frame to what's called a coherent reference frame. And that mapping is accomplished through a pair of deformation gradients FA and FB. And basically, if there's a closure failure in this coherent reference frame, which there is, of course, here in this schematic, that is the Burgers vector. So in order for ILDA to work, we need to know these deformation gradients. So but we didn't tell it a deformation gradient. How did it get that deformation gradient? Well, okay, so basically there's two methods for determining this CRF, or this coherent reference frame. The one is manually, which we'll talk about more in a second, where you manually specify it. The other is this automatic method. And so what ILDA is doing in this automatic method is it's estimating FA and FB based on atomic deformation gradients. So what ILDA does, is it looks at all the atoms within a distance dist F of the interface. So it's only using atoms very near the interface. It computes the deformation gradient of each of those atoms, and then it takes the average of all of those. And that's what it uses to get FA and FB. All right. The thing to keep in mind, so this is a very nice thing because it's automatic. So as you saw when I just ran ILDA, we didn't have to say anything about the interface, right? All I had to do was pick a pair of atoms and hit extract lines, and it automatically found the lines for me. But the problem is so this is using then the estimated approach for finding the CRF. But the issue is, because it's estimated, it's not truly coherent. There are closure failures even with the perfect crystals when you map them with these estimated deformation gradients. So now going back here, it prints what these deformation gradients are. Here's FA, here's FB. Okay. And then it's also showing what the polar decomposition is, which I'll talk a little more about in a second. So the issue is that what that means then is that the Burgers vectors are not precisely correct. They have some error. Every Burgers vector has a little bit of error in it. So that makes the Burgers vector statistical. So you can see that if you look, for example, here and here, okay, these two Burgers vectors are almost exactly the same, but not quite. They differ in the second or third digits. And that is why this is changing colors along here. So how do we deal with that? One is, we output the statistics, so you know what the variability is across all the Burgers vectors. But what we have implemented here is this parameter we call btol. And btol, so what ILDA does is it says every unique Burgers vector magnitude is unique. But if you have variation for the same along the same line defect, if you have variation in that magnitude, it's going to identify basically every single segment as being a unique Burgers vector, which is not true, right? It's just variation of on the same one. So b tall is the magnitude of difference which we ignore. So what we're saying with 0.01 is if the Burgers vector differs in magnitude by more than 0.01, we declare it to be unique. So what we can do then, all we have to do is just increase this a little bit to 1/10 of an angstrom. And now when we run it, it's gonna assign every segment to the same Burgers ID. So now you can see they're all the same color. And when we come down here, we've now found one ID. It gives us what the average is. It gives us what the standard deviation is. And also it reports step heights, average step height, minimum step height, maximum step height. Okay. Okay, now just to finish that out, there's a couple other parameters that are of relevance when we are doing this estimated automatic mode. The first is that distf parameter. So again, this is that parameter which says when it's computing these deformation gradients, what atoms do I use? So distf is the distance from the interface that is used, so 10 angstroms, so something like this. So only atoms within sort of this distance of the interface from here and up are being used to get that deformation gradient. So you can vary that a little bit to see if it helps reduce the variability in the Burgers vectors that you're getting out. You don't want to make it too big because A, it just runs slower, but B, because as you get further and further from the interface, your deformation gradient can become inaccurate. But if you include too few atoms, then it's also going to be inaccurate. So there's kind of a sweet spot that you've got to hit for this distf parameter. The other parameter of relevance is angtol. So the issue here is if we have, okay, so again, you'll notice that we have down here, the output, we have a variant column and an ID column. So ID refers to the magnitude of the Burgers vector. Variant refers to the direction of the Burgers vector. So what ILDA is trying to do is help you sort out what's going on by telling you, okay, all of these Burgers vectors have the same magnitude, but I found 3 distinct directions. So think of, for example, FCC 110 Burgers vectors, right? Every glide plane in FCC has 3 distinct 110 Burgers vectors that point in different directions. So what ILDA would do is assign all of them the same ID, and it would find that there are 3 variants. So what this angtol then is the angular tolerance in terms of the direction that the Burgers vectors point, which is used to group them. So in other words, if they differ in their angle by less than 5 degrees, so this is in degrees, then they're declared to be the same variant. So again, these parameters are just to help you kind of summarize what's going on in your interface. Okay. Then, all right, so that's how we use it if we want to do this automatic mode. But in many cases, you're going to actually already know what your coherent reference state is because let's say you manually construct the interface. So in the case of the simulation I'm showing you, we manually constructed the interface, or I manually constructed the system. So I already know what my coherent reference frame is. And in that case, it's the Nishiyama-Wasserman orientation. So in that case, you just tell it. And the way you tell it, so in the way to think about the coherent reference frame, it is the state of the crystals within which the 2 crystals are coherent somehow. So for example, it would be like a sigma orientation for a grain boundary. And so the way you have to specify that then is with so these Fs, they have a rotation matrix and a stretch matrix. The rotation matrix is simply related to how you have to reorient the crystals to get them to be coherent, right? You're going to take this crystal, rotate it some, take this crystal, rotate it some. And so you can make that rotation matrix by just specifying the orientations of the crystal in the interface. Then the other thing we need is a stretch matrix, and this is if you have a biphase interface where there's a mismatch between the two crystals. Then you can specify the coherency strains associated with rendering the interface coherent, and then it will, and so that basically you can exactly compute what these deformation gradients are. You don't have to do it, ILDA does it for you. What you have to do is tell it what the orientation vectors are and what the coherency strain matrices are. So let's enter that information, which I have written down here because I know it for the system. So for Nishiyama Wasserman, the FCC crystal has the x direction is 1 bar O. The y direction is, so here we'll just unclick that so it doesn't keep updating every time I make a change. 1, 1, 2 direction for the y. For the BCC crystal, it's in the x is already 1, 0, 0, and y is 0, 1, 1 bar. Okay, and then for the coherency strains, and this example is actually given in the manuscript, so you'll be able to see the case there as well. For the FCC crystal in the x direction, it's stretched with a strain of 0.0669, and in the y direction, it's got a strain of 0.0372. No strain in the z direction. In the x direction for the BCC crystal, it's minus 0.059, and for the y direction, it's 0.0401. Okay, so the only other thing we have to give it is the lattice parameters. So AA and AB are the lattice parameters. So once we give it all of that information, it will exactly know how to proceed with constructing the Burger circuit. So now we say extract lines, but we also have to now unclick this estimate F box. So this estimate F box is telling it to use the estimated coherent reference frame. Now if we unclick that, and it'll run, and it runs a little bit faster, and I hope I didn't make a mistake entering that so that it actually comes out correctly. Let's see. No, that doesn't look good. What did I enter incorrectly? Okay. I'm back. I incorrectly wrote down one of my things here. But anyway, this is a teachable moment, okay? Now, what you can see is that the interface looks like a mess. So if we just get rid of the particles, it looks like there's line defects everywhere. So what is ILDA doing? Well, I mean, it's doing what you told it to do, or what I told it to do, which is it's using this as the coherent reference frame. But the problem is this coherent reference frame isn't actually coherent. Or maybe it is, but it's not close to the way that the crystals are oriented in the simulation. So that is one of the limitations of this manual coherent reference frame right now, is that the orientations you put in here have to be close to how the actual crystals are oriented in the system. So in other words, the x direction has to be close to this. The y direction for the FCC. And so the issue is I'm missing a minus sign here. So if I put that minus sign in, run it again, there we go. So now we're back. And so what you can see, okay, but what's different? So first of all, it runs a little faster this way because it doesn't have to do the deformation gradients. But if we come down here and look at the output, you can see that the standard deviation is now 0. And the reason is because the Burger's vector is exact. All of the uncertainty we previously had was just coming from the fact that the deformation gradients that we used were estimated, and so we had closure failures. But here they're exact to within the numerical precision that we use to specify our lattice parameters and also our coherency strains. And so just to demonstrate that effect, so let's decrease this BTOL down to be very small. Let's see what happens when it gets that small. You can see even with a very, very tiny BTOL, we're still finding just one single ID. But if we keep decreasing it, eventually it's going to tell us that there are many unique Burger's vectors present. because we're getting to the precision at which we're determining them. And so again, yeah, here you can see there's line defects everywhere. It's a mess. And you can see all the different IDs it's found, but you can see a lot of the Burgers vectors are basically 0, right? All these zeros, and that's just because that's the precision with which the Burgers vectors are being calculated. And so anyway, that gives you a sense for how it behaves. So if you know your crystal orientations, and you already studied the interface, and you know how the crystals need to be oriented for it to be coherent, you can just run it with the manual mode and you will get exact Burgers vectors out. And again, if you run into this issue where you punch stuff in and there's line defects everywhere, it's because there's some issue with this particular reference orientation that you've given it. And so with that, I think that's everything I have. That is the end of the tutorial on how to use it. So I hope this winds up being a useful tool for the community. And so going forward, we have it released right now through GitLab, but Alex Stokowski is actively trying to figure out how to make it as easy as possible for people to develop and implement and use these Python-based modifiers. And so it's going to be a dynamic process in the future. But anyway, we're excited about the development of this tool, and we hope people find it useful. Thank you.